Okay, thanks, Bill. So I'm going to go talk a bit about the water aspect of the project and the model up it and so on. Bart Nyssen will follow. So there's a list of characters up here. The second on that list, Matt Stumbaugh, who's in the back there, is certainly the one who's done about 99% of the work. Bart Nyssen and our main role has been to sort of flog Matt faster, get those model runs done. And then the three students of ours at the end have been very helpful in pulling together a good deal of the graphics that you'll see here. So both Phil and John Appisklu have talked a little bit about the water part of this and how this all fits together. I'll give just a little bit of an overview here at the beginning about the hydrologic modeling and attempt to give you a little bit of background so you don't think that we just make all this stuff up. Because towards the end, I'm going to go through quite a few graphics of what the model output from the downscaled climate looks like, but I want to talk just a little bit first about the model that produces them and the historic data sets that kind of underlie this, and John mentioned them a little bit. So the hydrologic model is something called the variable infiltration capacity model. I won't go into details here at all. There's many, many papers on this model, and it's pretty widely used. It goes back to work done at the University of Washington in my group and in Eric Wood's group at Princeton starting in the early 1990s, when we found that for a number of purposes, including climate change assessments, there really were no hydrologic models that were well suited to modeling large river basins or even continental things. Were much more sort of smaller catchment based. So it is a grid-based model. The thing over on the right you see sort of a connect the dots type of network, and then each of those boxes is a grid mesh. For the purposes of these discussions, that grid box is 1/16 of a degree, just like the climate forcings, and the model represents in the subsurface 3 layers of soil moisture. It produces both the sort of direct runoff from the land surface, and then it produces a sort of slower base flow component, and then all those arrows at the surface have to do with water and energy exchanges. It is driven by precipitation, downward solar and long-wave radiation, and various other variables, surface temperature, wind, and so on. And again, I'm not going to go into the details, but in the end, it produces stream flow estimates at kind of the outlet of river basins, and then at each of those grid boxes, it produces a number of fluxes, the primary ones of which are evapotranspiration, runoff, and then certain state variables, soil moisture, and snow, which is very important to us in the Pacific Northwest. And there's also some energy fluxes, which aren't really so much of interest to us directly here. The model also has, very important for the western U.S., an energy balance snow accumulation and ablation model, which knows about vegetation. So it knows about the interception of snow in forest canopies, an important process, and then how that snow gets sort of underneath the canopy and what the dynamics of the snow are. The underlying historical data set, and John mentioned this, is described in a paper that just came out late last year by Ben Livna, now a postdoc at the University of Colorado, previously a PhD student in our group, and a number of people in my group, including Bart, myself, and various current and past postdocs and graduate students, described this data set, which is also at 1/16 of a degree. It is an update of something called the Maurer et al. 2002 data set, which was at 1/8 degree spatial resolution across the continental U.S., and it had a set of both downward forcing variables, gridded precipitation, temperature, daily min and max, wind, as well as downward solar and long-wave radiation, and so on. That data set has been pretty widely used. It says here 300 and something Web of Science citations. I think that's in the 400s now. But the data set was for the period 1950 to 2000 and had become pretty out of date. We had run, as part of that data set, not only the forcings were provided, but a number of derived variables, downward soil and long-wave radiation and so on. Whoops, if I wave my hands, the thing advances on its own. And then derived variables from the VIC model. Okay, this is being runoff and soil moisture and so on. The same variables I mentioned earlier, but these are historic reconstructions. So that data set has been out there since 2002 or so. The LIBNA effort basically updated that for a period that goes back to 1916 or so and goes forward to 2000 and I think it says 11 now, but it also is being extended actually up through 2013. So that's kind of the domain. It's the continental U.S. and the part of the Columbia River Basin that heads in Canada, which is important to us for this particular project. So one of the things I want to say here just very quickly is to give you some sense that we have made efforts to go compare the historic reconstructions from VIC using the observed forcings with observations. And this is for sites, the surface energy balance sites across the U.S. where these things are measured in great detail. If you look at these things closely, the model plausibly reconstructs things. These are the mean diurnal cycles for some part of the year. Many more details of this. Over to the right, you see where those locations are, more or less band across the U.S., and you can read the paper, and there's many more details of that. Other things, hydrologic state variables, mean daily precipitation, things like soil moisture, snow water equivalent, and so on as distributions match reasonably well. Simulated river discharge for a number of points, and if you're in the back of the room or even looking at the screen as I am from here, those look pretty good. But if you move a little bit closer to it, you see that there are discrepancies, and the one thing I think is important to keep in mind, that even for these large river basins, the historic model reconstructed variables are not going to match exactly the observations. Phil sort of mentioned that just in the context of precipitation and some of the other forcing variables, and it's certainly true for the hydrology, and you need to keep that into account and not have the expectations that there will be an exact match. On the other hand, there is sort of plausible reproduction over large river basins. This thing does want to advance on its own. I guess I should talk faster. Soil moisture is something we've looked at the relatively few number of sites where there's multiple decades of soil moisture observation. One of these places is Illinois, which has a statewide soil moisture network. What you see in the upper visual is that the observed and the simulated have a very similar seasonal cycle. There's a little bit of an offset. That's not at all unusual for land surface models because the characterization of soil moisture and what actually goes on are somewhat different. But the persistence of the soil moisture in the lower visual there is really quite similar between the observations and the model reproductions. And I think one thing that's kind of interesting there that John mentioned in his talk this morning about the time sequencing of climate variables in the climate models, even precipitation, that does get reflected in the model output, in the hydrologic model output. I think what figures like this sort of suggest is that to the extent that there are discrepancies in some of these variables in terms of time sequencing, persistence, and so on, droughts and all of that, it's probably more likely to have to do with the forcings and issues there than it is with the model itself. That's what I take away from figures like the bottom one. This is from the Mode et al. Declining mountain snowpack in the western U.S. And what it is over on the left, those are historical trends in snow water equivalent, and over on the right is what the model did. This is for an earlier period, earlier version of the model and so on. But the important thing is, again, if you're sitting in the back a ways, those look pretty similar. The models reproduce surprisingly well, observed snowpack characteristics and even trends in the snowpack. And then there's another figure out of that paper which has to do with how trends in the observed snowpack across the western U.S. vary with sort of a surrogate for elevation, which is a mean winter temperature, and that's what those sort of profiles are. Shows both the model, and the model has lots and lots of pixels, and the observations are only at certain points. But if you look at kind of the mean of the model for a given elevation across these different partitionings, the Cascades, Rockies, dry interior in California, for the most part, they're pretty similar. The reproduction is not too bad. So while I don't want to leave the impression that the model doesn't have any warts, because those of us who work on it know what's under the hood, and we know of lots of little issues. That's true of any model. But take it as a whole, it does a plausible job when it's given decent forcings of reproducing hydrologic observations. So let me move forward now and talk about what we've actually done and are doing as part of the Integrated Scenarios project. So the VIC model, as we're running it, is the same as in the LIVNA 2013 data set, same version of the model, and it is an update, and there's a variety of things that have changed since 2002, not surprisingly. Just like climate models evolve, land surface models evolve as well. The domain is the continental U.S. plus the Canadian part of the Columbia River Basin, 1/16th degree. Model initialization, this is important for hydrology models where they're, unlike the atmosphere where there's not a lot of storage, so there's not a lot of persistence in what goes on, because of subsurface storage and storage, soil moisture and storage of moisture in the snowpack, you have to be a little bit careful how you initialize things. Typically, you spin things up for some period of time. And basically, what was done here is the model was initialized using 1940 to 49 from the LIVNA et al. Data sets, and then was run forward using the downscaled climate model forcings for the period 1950 to 2006, and then it runs forward with the scenarios essentially seamlessly through the historical period and on into the future. So one thing that's important to keep in mind in terms of what's being done here, and John talked about this a bit, but so the MACA downscaling method is what's producing all our forcings. So John's group has run MACA, produced all the forcings, ported them over to us, and then we use them to go force the VIC model. Each of the climate models has an historical period, which is 1950 through 2005, I believe, and MACA is used on that to basically take care of the bias and to do the spatial downscaling. So what happens is the historical model run for those 55 years statistically looks like the historical past, but any individual year is not going to match the historical past, is not expected to. And I'll show you sort of some of the effects there. So what gets archived is the model's 55-year historical period, which is statistically similar to history, and then that transitions on into the future for the two RCP scenarios. So what we've done is to archive, and we do this, Bart will talk about this a little bit more, but we archive daily and monthly runoff, and there's actually two terms of surface and the base flow. Most people probably just want to add those together. Snow water equivalent, evapotranspiration, soil moisture are the three levels in the model. Many people are just going to add those together for total soil moisture. And then precipitation, which is identical to what John passes us, but it's good to have it in the same place and doesn't take a lot of storage. So then the output variables in addition are, all the moisture fluxes, the surface energy fluxes, and so on. I'm sorry, the final point, the output. There's a number of output variables that come out of the model that we don't actually archive. We archive the set that I mentioned above. That's sort of a fine point for most people in the audience, but perhaps there's somebody who really cares about emitted long-wave radiation, reflected solar, surface temperature, not air temperature, but the surface soil temperature and so on. And if there really were a demand for that, that's something we could talk about. We're not actually archiving those at present in the interest of space. So the domain, and I think either Phil or I or John mentioned this for the hydrology. So the macros run across the whole continent U.S., but we're running west of, I believe it's 102 longitude, which is everything in white plus the colored part. The colored basins, we have saved variables, and I'll actually be discussing some of this by region, although I'm going to focus mostly on the Pacific Northwest in red. The upper Missouri Basin, we've actually also archived separately some of the information for, not shown there because of a graphical mix-up, but it's not the entire Missouri. It's a part of the Missouri above the edge of the white, and it turns out the upper Rio Grande's in there as well. If there's, I'm assuming this audience, there's not so much interest in that, but we have interactions with the Southwest Climate Science Center, for instance, which presumably is interested in some of this. So what I'm going to show in most of the rest of this is a whole set of visuals, which they start looking the same after a while, but trust me, I got hundreds on my laptop, and I've tried to winnow them down to some number that people won't go blind looking at them. So we have these things by basin, and the basin results I'll show only the Pacific Northwest. Again, if anybody's particularly interested in, say, the Colorado River Basin, those things are around. We have the entire domain, which is everything in the west. We have spatial plots, and again, these are the historical period is not what we're showing here is the 30-year period, 1971 to 2000. That's kind of of particular importance in the U.S. because of reference climate period, even although the model runs the longer period. Mid-century, 2040 to 2069, late century, 2070 to 2099. Part of the reason for doing 30 years for the historical is that it's then consistent with the two future time slices we're looking at. Multi-model averages, we are running 10 of the models, and these are the 10, quote, best models from David Rupp's work. We're actually talking about doing the full suite of 20. We're actually sort of obligated. When Phil wrote the proposal and we thought about, oh my God, how much computing is this all going to be? I think we said we'd do 10. We have results for 6 of them I'll show here. So when you see multi-model averages, they're results for the first 6. We actually have, so this is all happening in real time. We have 8 of them done as of now, and I'm assured by Matt by next week, all 10 of those will be done. We're pretty close. And so keep in mind, since these are averages of 6, if you see something later on that shows a multi-model average and it's different, that's the reason. And 6 versus 10 can make quite a bit of difference. It actually turns out the first group of models we've done tend to be somewhat on the wet side, and that does influence the results a little bit. We have available snow water equivalent, total column soil moisture, runoff unrouted in ET. I'm not going to show ET results, but I am going to show snow water equivalent because that's such a dominant variable in the Pacific Northwest, as well as some of the soil moisture and runoff. And I'll show stuff on the domain average seasonal cycle, and then we've also got some time series. Okay. So now this is what the western U.S. for the whole domain suite looks like with a threshold of 10 millimeters, and it's the average for April. In the future, what we're going to archive is the first of the month stuff because of some confusion. We have monthly average here. That's not going to make a lot of difference in terms of qualitatively what happens. So there's the multi-model average, RCP4 and RCP85. The problem is when you look at it this way, it's a little bit hard to see what's changed, even though there are substantial changes. So if you go and look at percent changes for the mid-century period for RCP 4.5 and 8.5, so the reds are big changes, the white, big negative changes, the whites are basically no change, and blues, if you look really closely, there are some blues. I'll show you some changes where we look at the changes in millimeters here in a minute. There are some areas where it actually increases, but with this color bar, they kind of get incorporated as percentages into the white. The picture there, though, is that if you had the elevations along side of that, the places where there are white basically are high elevations, where it's relatively cold, particularly the Canadian part of the basin. You don't see too much in the way of changes. Pretty deep snowpacks. The percentage changes are pretty small. Where you see big changes, lots of reds, are where there's on average relatively thin snowpacks, transient rain on snow zones, where those virtually go away. And if you go look at this in terms of the change in millimeters, it's kind of interesting. You get a whole lot of little specks there. And the big changes now, where you kind of got 100-meter-ish changes, are actually the higher elevations. 100 millimeters in many of these places is a relatively small percentage, but it's a substantial amount of water equivalent. And then the lower elevations, even in some places where the snow is wiped out, since the threshold's 10 millimeters, what ends up happening is on a scale that's kind of going down to minus 100 and so on, a 5 or 10 millimeter change kind of looks like white, like not much of a change, even although it may be enough to make the snow essentially go away completely. So there's the main picture here is that the high elevation changes are fairly modest, essentially as percentages. The low elevation changes tend to be much larger, certainly as a fraction, and some of that snow goes away entirely. There's nothing really new here in that finding. That certainly has happened in the CMIP3 results as well, because it's largely dominated by temperature change and changes in the snow line and the accumulation of snow, less snow accumulating in the winter. For the Pacific Northwest, same thing. It's a little bit hard to tell what's going on when you just plot the distribution, but this is just blown up from the previous one. Whites, high elevation, lots of snow. Reds, lower elevation around the edges. Same thing when you go look at a fixed threshold. So for soil moisture, I'm going to show March and August soil moisture, and I'm showing these only as changes. It's a little hard if you just plot the soil moisture to understand the magnitude of the changes. This is total column. Over on the left, it sort of shows the distribution. It's not too surprising that big blue numbers are out along the coast where there's lots of precipitation. Brown numbers are in the interior where there's less precipitation. But what's kind of interesting is that over a good bit of the domain, and there's something funny's gone on in the upper right there in RCP 8.5, which is a data issue of some kind, you see kind of a preponderance of blues. And I think there's two things going on there. One is, on average, and I'll show you in a few minutes, these tend to be a wet group of models, and this is an average over these 6 models. So, and that increase in precipitation is mostly winter and spring, which is when the precipitation happens. So it gets wetter. There's not much evaporative demand in the winter, makes things more moist, higher soil moistures. The other thing is that less snow is retaining less of the moisture in the snowpack and putting more of it into the soil column. So it tends to get wetter in March. Now, if you go forward and look at August, you get kind of a more interesting picture. And what you see is reds that are mostly high elevation, and those are places where the snowpack has been reduced substantially, and what's happening is the snow's going away earlier in the year. This is my take on it. Goes away earlier in the year, goes away in the summertime when the evaporative demand is relatively high, so it's got a longer period to go extract the soil moisture, and it ends up getting drier than it was in the previous climate. Some of the blues at the lower elevation, and it's not all blue, there's a lot of white in there, which is relatively unchanged, but there's, if you don't see whites, you tend to see blues at lower elevation. I think that's kind of a carryover effect from higher precipitation in the winter and spring that's carried through to August, at least in some of these cases. That the ET demand, which actually has gone up a bit in the future climate, is not quite enough to go take out that extra moisture that's accumulated from the precipitation. And the same picture basically in more detail for the Pacific Northwest. Lots of blues in March, and then this pattern of sort of high elevation reds decreases and some lower elevation. It's kind of interesting what that bullseye sort of in eastern Washington is about, and I'm guessing that that's going to be traceable back to precipitation anomaly, but we'd have to go take a look to go understand that more carefully. So show now, this is sort of the mean seasonal cycle of historical precipitation from these different models, and then the multi-model average, which is black. And so this is kind of an example of what I showed before, that each of these models is mapped back with MACA. So this is coming straight out of MACA. This has nothing to do with the hydrology model. They're mapped back so as to take the bias out, but because of differences in the manifestations for these individual models and the time sequencing, you get this sort of variability. Statistically, you can actually show, and I've done this in the back of the envelope to convince myself that that's true, that these aren't statistically significantly different. It's kind of like different ensemble members drawn from the same population, but you do get reasonable amount of bouncing around from the historical downscaling from these different models. This is the Pacific Northwest, kind of more of the same. I mean, there's more precipitation, not terribly surprisingly, and things bounce around a little bit. Now, if we look at, and these are multi-model averages now over the entire western U.S., which shows the precipitation historical in the upper plots, and the lower plots are runoff. And so what you see, the black is generally below the red and the blue, which are the mid-century RCP 4.5 and 8.5, higher precipitation, and that's driving a lot of what's going on. For the runoff, not surprisingly, it's warmer, so you see that the cycle has moved, the peak of the runoff has moved earlier in the year, typically by a month or even 2 months. One of the things we're going to do, we're looking into using pentads for some of this and possibly archiving a pentad data set. The monthly is a little bit too long to really pick up these shifts, some of which are order of a month or so. And then this is the same thing for the Pacific Northwest, and there you see this precipitation increase in the winter especially, but clear on through the spring is a little bit accentuated there, and you do see the shift in the runoff. Again, nothing terribly new there. The one thing that is kind of interesting, and I'll show this in a different way here, a couple of visuals down the line, is that if you integrate under the runoff curve, the differences between the blue and the red and the black. So what is the change in the annual runoff? It's actually pretty close to zero. Okay, mostly this is about a timing shift. And okay, so this is basically the same kind of plot, but it is for RCP, I guess, 8.5 only, but it is for mid-century and mid-century and late century. Thank you. 2040, 2069 runoff. Yes, runoff. Okay, thank you. Got to read those and make sure that that's what that is. And you can see, I mean, it's kind of interesting that in the precipitation, the mid-century precipitation and the late century precipitation aren't too much different. And I don't understand the fine points of that, but I'm not sure I want to get too mixed up in that because it's a 6-model average. When we get to 10 models, we'll probably pay a little more attention to that and explaining why. Okay, so one of the last things we did was to look at the actual time sequences of both precipitation and runoff. These are multi-model averages, and it's a moving average also to knock out some of the year-to-year variability. So the thin line across there in both cases is the average of the historical period, mostly just so you can see what's happening in the future. And as in the mean seasonal cycle plots, you can see that the annual precipitation in general is going up. And in the end, it goes up, even though there's decadal variability and so on in there. It's actually about the same for RCP 4.5 and 8.5. What's interesting, though, is when you look at the runoff, you don't see too much change in the future period in the annual average. Yeah, there's decadal variability, and maybe you can imagine something's going on there with RCP 8.5 going down towards the end, but then it bounces back up. I don't know if that's real or not. And again, once we have 10 models in there, we'll probably pay a little more attention to this, but there is this dominant characteristic with these 6 models of increased precipitation and more or less flat runoff. This is just the same plots for the individual models. Those averaged together lead to the one that I showed previously. And so for most of the individual models, you don't see too much change in the runoff. Elsewhere in the West, there is, particularly as you go further south into the Southwest, evidence of declining runoff. But what is kind of interesting is that there's been a whole lot of hoopla over the Colorado Basin from the CMIP 3 results of declining runoff. And there is some evidence, even from taking the larger set of the models and just taking the output from the global models, that signal is muted a little bit. It's still there some, but it's muted a little bit in the AR5 runs. And then finally, this is just the snowpack. I'm showing this only over the Pacific Northwest, and what you see in there is the RCP 8.5, which is the red, decreases more than RCP 4.5. You'll see, as I commented this morning, that until about 2050 or so, they kind of bounce around up and down. There may be something going on in here with these models being a little wetter, that there is some compensation, and there's actually some evidence of this in the Upper Columbia, which has slight increases in snowpack at the highest elevations. If you go back to the visuals I showed, and you look at them real closely, you actually see that. And then that effect, as you go further into the century, gets sort of overtaken by the warming and everything starts going down. But this is not surprising. In fact, if it didn't look like this, we'd be worried. Okay. So just to sort of wrap up, these are summaries of 6 models and 8 now done, 2 more in the next week or so. We're getting pretty close. There are no big surprises relative to AR4. This business signature for the extratropical drying is muted somewhat. That is more applicable to places like the Colorado and the Great Basin. That didn't really affect the Pacific Northwest that much anyway, even the CMIP 3 results. As before, the main signature of climate change in the Pacific Northwest hydrology is reduced snow. That's affecting dominantly the timing, and there's also substantial effect spatially of the soil moisture, but superimposed on that also is this effect of, at least in these 6 models, some wetting. And then the annual streamflow volume changes so far are generally smaller, relatively small, and I interpret that as being the fact of increased evaporative demand is more or less being balanced by increased precipitation, and there's a bunch of timing issues all sort of mixed in there. So I'll stop there.
Hi, Dennis. This is Tim Mayer from U.S. Fish and Wildlife Service, and I had 2 questions. First, I assume that this will eventually be available, gridded data, kind of covering the region, if it's not already. Is that true?
Yes. In fact, the next talk, whenever that is, by Bart, is going to describe the archiving and so on. I purposely left that part out.
So I had a question about that. If I go to a point, a stream gauge, and say it's heavily impacted by regulation or diversions or something, is your modeled historic and modeled future reflecting that land use, or is it kind of, potential hydrology like we were talking about potential vegetation?
Yeah, short answer is no. What it's doing is it's using historical land cover, and it runs the historical land cover through the whole future period.
Just kind of assumes static, whatever's there, then you're kind of adding the climate change signal on top of it.
We're adding the climate change signal on top of that. Now, we've actually done quite a bit of work looking at land cover change signals and so on, and there's work over the Puget Sound Basin comparing the signature of land cover change over the last 100 years as contrasted with climate change and so on, but that's not at this point reflected in here. I think the work we saw earlier this morning about future vegetation change and so on, the next step is to link some of that in, which is in principle easily done, but hasn't been in the stuff we've done so far.
Okay, thanks.
Yeah, you got someone over here. Yeah, keep going. Oh, yeah, whatever. Saw two hands there, but.
Yeah, Dennis, Steve Klein, EPA. I had a question about when you mentioned the routing part of the model that the data hadn't been modeled, the routing part of the VIC model hadn't been implemented. Was I correct in taking that as what does that mean as far as the available data?
Yeah, so what I showed here was unrouted runoff, where we just added up the grid cell runoff over the entire domain and showed that. I have to look to see what we have agreed to do. We have a routing model, and routing to sort of fixed points in the domain is relatively straightforward. We may well have promised to do that. Bart, do you remember what we're doing there? I mean, okay. I mean, it certainly is possible to do that. It's not too likely that we're going to run down to sort of route at Huck 8 scale or something, but the major flow points in the Columbia and some of these major river basins, we do have those, and I'm guessing we'll probably do something along those lines. At monthly time steps, you can figure out that the lag times are pretty small, so the run-up you can take directly.
Ethan Rosenthal with David Evans and Associates. I was just wondering, so the Climate Impacts Group did something similar to this a few years back?
Yeah, this is a so-called 2860 project, I think, that Alan Hamlin.
Yeah, so does this supersede that work?
Basically, yes.
Okay.
Yeah,
okay.
Because that was CMIP3 or AR4 model output. Okay. And there's a certain amount of heritage that's been incorporated from what was done in those days in terms of model parameters and so on. It turns out the version of the VIC model is more up to date and so on, but essentially you should view it as the next step beyond that data set.
Thank you.
Dennis, how do your results figure into the Columbia River Treaty?
Funny you should mention that. It turns out we have an ongoing project funded by BPA to deal with exactly that issue. And the starting point for that project, on which Bart happens to be the lead, are the simulations that we're doing here. There's some, model improvements, incorporation of a glacier module that they were particularly interested in for the headwaters of the Columbia, and various other sort of bells and whistles, but essentially it's a leveraging from what's being done here. Phil is also involved in that, I might point out.
Hi, Dennis. I have 3 questions from online folks. First one is from Paul Pickett. Are glacial melt and disappearance included in the modeling?
Okay, so the answer to that is no. At the scale of the region, it's not that big a deal. However, if you want to go study headwaters of the Columbia Basin or whatever and are particularly interested in summer flow, it's not, that effect's not reflected in there. However, if you stay tuned for another sort of year or so, after we have results of the BPA project out, there will be derived data sets that include the glacier contribution.
Okay, and the next question is from Patricia Olson. If you could go back to the slide that shows the different model runs. The question is about the historical data having different moving average patterns among the models. Is this because the historic data were also modeled so they reflect the model differences.
So my problem is I can't find home on this keyboard. Control. Is there no home here? I just want to go to the beginning. Control home usually does it, but okay. That's not all the way back. So I'm sorry, the question was about the update from the previous data set. I think it was the
about the
model runs. Whoops, integrated scenarios hydrology?
I think it was about the historic simulations for, like, the time series you had.
Yeah, and why they aren't all the same?
Right,
So they're probably these plots?
No, I think it's...
no, keep going.
These.
Oh, okay.
Yeah.
Okay. So can you give me the short version of the question again? Sorry.
Yeah, I'm trying to interpret it. So
the historical, what's shown there is historical model. It's not.
It's historical model, and it's the multi-model average. So I made this point of these different historical periods in the macro mapping aren't identical because there's kind of random variability in there. But this is averaged across those. So yes, it's the historical model. And I think John mentioned this for some of the climate variables, and I would emphasize the same thing here, that because there are model biases, notwithstanding that we try to minimize those, it's important that you compare future simulations with the model reconstructed historical and not the observed historical.
Okay, and from Don Phillips, there appears to be a contrast in August soil moisture at the U.S.-Canada border.
Yeah.
Is that just a
I'm the
difference in
first
data
one to
set?
notice that. We, however, had never noticed that. No, I mean, this has sort of been driving Bart and me nuts for some time. The reason is that the parameters of the VIC model, as you can imagine, trying to find soil moisture characteristics in databases, which for the U.S. come from the USDA. They don't know about Canada. The Canadians have something else. And so there's a discontinuity there. And there will, in fact, be a version 2.0 or 1.1 or something of the model that is going to take that problem away. But, yes, there is a discontinuity in there.
And then one final question from Paul Pickett. You showed a lot of results available at the large-scale level, Columbia. Will they be scaled down further for smaller basins like Yakima River, for example?
Yes, maybe, and I think Bart's going to talk about that. We have been discussing giving sort of average results at some smaller spatial scale. Anything else? Okay.